All right, so we have next up in line section 4.8, which deals with the concepts of rank, nullity, and fundamental matrix spaces. Now recall that the dimension of a finite dimensional vector space, V, remember, is denoted by this dim of V. And how did we define the dimension? It is defined as the number of vectors within the basis for V. Right, so the dim of V counts the number of vectors in the basis for a vector space V. What is a basis again? It's a set of vectors. Firstly, that the span of which is the vector space, and the vectors within this basis have to be linearly independent. Now also we said, in addition, the zero vector space is defined to have dimension 0. Right, next we have theorem 1. This theorem we already touched on. The row space and the column space of a matrix A have the same dimension. Why is that? Because previously, how did we determine a basis for the row space? We took a matrix A and we reduced that matrix to reduced row echelon form. We looked then at the rows containing the leading ones. The leading one rows formed a basis for the row space of the matrix A. Then, how did we determine the basis for the column space? Again, the column space of a matrix is the space spanned by the column vectors of the matrix A. And how we did this, again, we reduced the matrix to reduced row echelon form, and then we looked at the columns containing the leading ones, and the leading one columns, the columns in the matrix A that correspond to the leading one columns in the reduced row echelon form, they formed the basis vectors for the column space. Now, if you can easily see that the dimension of the row space and the column space is the same, because the row space depends on the leading one vectors in the reduced row echelon form, and the column space also depends on the leading ones contained in the columns. So it's all about the leading ones. So the number of leading ones is going to influence the dimension of both the column space and the row space. So they both have the same dimension. So therefore the common dimension of the row space and the column space of a matrix A, we define that as the rank of the matrix A, right? And it's denoted by that quantity there. The dimension of the null space of a matrix A. Now, what was the dimension of the null? What's a null? When is a vector in the null space of a matrix? Recall that a vector x bar is in the null space of a matrix A if it satisfies this homogeneous linear system. Right? So if you look at the null space and you go and find a basis for that null space, the dimension of the null space, which is determined by the number of vectors in the basis, that is called the nullity of a matrix A. Okay, so I want to just go, before we carry on, I just want to go back in time a little bit and just go and investigate the null space again. So remember we talked about this linear system here. So we want to determine a basis for the null space. Now, right, so what we're going to do is we're going to look at each component separately, A, X bar, and 0 bar. Right, so there we've got the matrix A. It's an m by n matrix. There we've got the x vector. And there we've got the 0 vector. Okay. So when traditionally, when we determine when we want a basis for the null space, it boils down to solving finding the general solution of that homogeneous linear system. Right. So putting all of that together, we get the following. Okay, and from there we can set up a linear system, a homogeneous linear system. And the process involved taking this matrix here and finding its reduced row echelon form. Okay, so the reduced row echelon form for the matrix A looks something like the following. Right, so there's a representation of the reduced row echelon form. And for argument's sake, we've got R 0 rows, and we've got M minus R rows with leading ones. Alright, so how did we find our general solution again? We used the reduced row echelon form. If we go back to the reduced row echelon form quickly and investigate that, we see the leading ones in the first M minus R rows, right? The leading ones there, each one leading one corresponded to a particular variable. And those were known as the leading variables. Now, of the leading variables, whatever variables remain, those were called the free variables. Okay, so we said how many leading variables are there? The number of leading variables, we said we counted that as m minus r. And how many free variables are there? Remember, the free variables, we assign parameters to them. So there are how many free variables? Okay, so the number of free variables is simply going to be calculate that by taking all the number of variables and from that number subtracting the leading variables. Right, so we get that's the number of variables we said was n, and from that we subtract m minus r, so that becomes n minus m plus r, and let's for argument's sake just call that whole thing q. Alright, so next, so the general solution for the homogeneous linear system AX equals 0 is going to look something like this. Okay, so there, so we set the number of leading variables is m minus r, and the number of free variables is q. And remember, we said q was the number, we got q, or the number of free variables is simply the total number of variables, which is n, minus the number of leading variables, which is m minus r. When determining the general solution, remember we assigned the free variables parameters, and then the leading variables, each one of them we solved as a linear combination of the parameters, which goes from T1 up until TQ. Okay, and each one of these leading variables we solved as a linear combination of the free variables. Okay, so there we've got the solution vector. Remember, we want to find a basis for the null space of the matrix A. So so there, remember, just to recap, those are my leading variables, and the remaining variables we already assigned parameters to. So doing the substitution, we obtain. Okay, there we've got the substitution, And let's just verify quickly that it is in fact true that this vector here is a linear combination between these listed vectors here. And it's for us to do that, go back to my original solution. All right, so just check quickly. There's my original general solution. So if we sum over all the first components there, that's T1C11 plus T2C12 up until TQ times C1Q. So there we go. We have all those terms. Then we take X2, sum over the second component, T1C21 plus T2C22, up until TQC2Q. TQC2Q. And we do that up until the M minus rth component, T1CMR1, there, plus T2CM minus R2, up until TQ times CMRQ. All right? Okay, and then summing the remaining components there, T1, we get T1 there. The second component we get there, and the last component we get there. So clearly that's equal to. Now, we are well on our way to find a basis for the null space. All right, now note that the variables x, the vector x1, x2 up until xn is in fact a linear combination of these vectors here. A linear combination of those vectors there. So first of all, those vectors are going to form the basis vectors. So I just need to check that they are linearly independent. Right, so we take my first vector there, label that v1. We take our second vector there and label that v2. Go up until we get the last vector there. We label that vector VQ. Okay, so we need to check that those vectors are all linearly independent. So we set up our linear independence equation and we get the following. Right, my first vector. Okay, my second vector, we do that up until the last vector, right, so we get our final vector there, and that all has to be equal to the zero vector. So now we can go and solve for my values k1 up until kq. Right, so to do that, again, it's very, very straightforward. First of all, note that k1 times that component there has to be 0. k2 times that component there has to be 0. And up until the last one, kq times that component has to be 0. So therefore, k1 up until kq are all 0. So therefore, the vectors v1 up until vq are linearly independent as well. So every vector in the solution space is a linear combination of the vectors v1 up until vq, and the vectors v1 up until vq are all linearly independent. So a basis for the solution space is the set B, where B is v1 up until vq. So the dimension of the solution space is Q, where Q is, so dimension of the solution space is Q, where Q is n minus m plus r. Okay, so let's just go back to our original system. So looking at our original system and the reduced row echelon form, so what was the rank of the matrix A again? The rank is the dimension of the row space, and the dimension of the row space is determined by the number of vectors in the basis, and the number of vectors in the basis for the row space is simply the number of rows with leading ones, and there are m minus r such leading ones. So the rank of the matrix A is, right, so there's the rank. And what is the nullity? The nullity is the dimension of the dimension of the solution space to the system AX equals 0. Right, so the nullity of A is we said was the quantity Q. Okay, and what was Q again? All right, so there the nullity is the dimension of the solution space is n minus m plus r. Right, so for future reference, I just want you guys to make the following observation. So if we take the rank of A, right, and we take the nullity of A, and we take the rank and we add it to the nullity, we get n, right? And what was n again? Going back to our original system, n signified the number of columns of the matrix A. So therefore the rank and the nullity of a matrix always add up to the columns, a number of columns of the matrix A. All right, so taking all of that and writing that down formally, that gives us Theorem 2, which says that if A is an m by n matrix, then the rank of the matrix is just simply, remember, the number of leading variables in the general solution of AX bar equals 0 bar. And the nullity of A is the number of parameters in the general solutions. In other words, the number of free variables. And again, the dimension theorem for matrices simply states that the rank and the nullity All right, so just there as an example, we are asked to find the rank and the nullity of the following matrices. So I just want to look at number 3. Number 3, if you take if you use Gaussian elimination, you see one sees that one gets this matrix here, and so so we can easily find the rank in that case there, because the rank is determined by the dimension of the row space. And these three vectors here form a basis for the row space. So the dimension of the row space is, right, so the rank of that matrix A can clearly be seen as 3. And what is the nullity? We don't have to go through that whole long process. The nullity is simply, remember, the rank of A, all right, plus the nullity of A. We said that's equal to the number of columns of the matrix, which is 3. All right, so we can easily solve the nullity as 3 minus the number of columns, which is 3, minus the rank of A, which is 3, which is 0. Okay. All right, so let's quickly look at number 1, which is that matrix there. And that matrix happens to actually be, if by closer inspection, that matrix is actually the matrix, the transpose of A. All right, so to find the rank of the transpose of A, we need to find the dimension of the row space of A's transpose. Alright, so to find the dimension of the row space of A's transpose, we can actually use the matrix A to do that. And we're going to find a basis for the column space of the matrix A, because the column space, the space spanned by the column vectors of A is the same as the space spanned by the row vectors of A's transpose. So we just want to find a basis for the column space of A. To do that, we already have the the reduced row echelon form of A, which is that. So those are the columns with leading ones are going to identify my basis vectors for the column space. So the columns with leading ones are column 1, 2, and 3. So therefore, the basis for the column space of A becomes the column vectors of the matrix A, all of them. So there's my first vector. There's my second vector. Right, so that's my third vector of my basis for my column space of A. Okay. Right, and I'll call the basis of my column space of A, I'll call it B subscript CSA. Right, so continuing, we have that the dimension of the column space of A is, dimension of the column space of A is 3, and that is equal to the dimension of the row space of A's transpose. Right, so that will then be the rank of my matrix A's transpose. All right, and therefore the rank of A's transpose is 3, and from that we can get the nullity, which is, right, and from previous knowledge, we know the rank and the nullity always adds up to the number of columns. So the nullity of A's transpose, therefore, has to be the number of columns minus the rank of A's transpose. So therefore, that is going to be 4 minus 3, which is equal to 1. Okay. All right, so labeling my second question, the matrix of my second question as A, we can go and then quickly reduce that by taking the first row and adding it to the last row. And then we can take minus 2 the first row and add it to the second row and get my reduced row echelon form, which is that matrix there. So what is the rank of A? The rank of A is determined by the dimension of the row space. Now, this vector here forms a basis for the row space. So therefore, the dimension of the row space is 1. Right, so there we've got the rank of A is 1. What is the nullity of A? Nullity of A can easily be determined. The nullity of A is the number of columns of A minus the rank. So it's the number of columns of A, which happens to be 3, minus the rank, which happens to be, in this case, 1. So the nullity of the matrix A is 2. Okay, so let's look at another example here. Here they just ask us find all possible values of the rank of A, where this small a is a variable. Right, so that's not a terribly difficult problem to consider. We are just going to merely find the reduced form of A. So let's quickly do that. Okay, so basically from there, we are going to take the first row, multiply it with minus a, and then add that to the third row. And so we get, okay, so there is our first reduction. Then we're going to take half the second row and add that to the third row. And so we get, okay, so now we have to consider a few cases. Right, so the first case, if a is -1, then the reduced row echelon form becomes the indicated matrix. Now, it's clear that from that we can see that the dimension of the row space of the matrix A, for the case where A is -1, the dimension there is 1. So the rank is 1. Right, so for case 1, obviously, the rank of A is definitely going to be 1. Alright, the second case is where A is not equal to -1. Right, so for the case 2, we have, right, so there we've got our reduced row echelon form, and take note that we can just factorize as that. Right, so we have to just consider the two cases there. That is case 2.1, case where A is 2, then we've got then if A is 2, we pretty much get what? Our matrix then becomes the following. Right, so that's my when A is equal to 2, and therefore the rank in this case for A equals 2 of the matrix A is clearly 2, because the basis for my row space is pretty much these two vectors here. So the dimension of the row space is 2. Then case 2.2 is when A is not equal to 2, and in that case our matrix becomes, alright, so there's the reduced row echelon form. How many leading ones are there? There are 3 leading ones. So the row space is going to have dimension 3. So the rank of the matrix A for this case is going to be equal to 3. Right, so to basically recap all of that, we have the following. Right, so the rank of A is 1 if A is -1. The rank of A is 2 if A is 2, and the rank of A is 3, provided that A is a real number with the exception of -1 and 2. Alright, so basically we can go and extend the equivalence theorem. Remember in the previous lesson we extended the equivalence theorem with all these properties here, and we can now go and extend it with these two properties here. Now a matrix is n by n matrix is invertible if and only if that matrix has rank n. What does it mean for the matrix A to have rank n? It means if you go and look at its reduced row echelon form, its reduced row echelon form has n leading ones. The only way that can happen is if the reduced row echelon form of A is the identity matrix In. And that happens only when A has rank n. Now when A has rank n, that is going to force A to have nullity 0, because the rank and the nullity always add up to the number of columns, and because the matrix A is n columns and the rank of A is n, that is going to immediately force the nullity to be 0. So that's pretty straightforward. Right, so the next little part is on overdetermined and underdetermined systems. That is self-study. You guys need to go through that on your own. It doesn't mean if something is self-study that it isn't important. It's also important, but that's left for you guys to go through on your own. All right, so the next part deals with fundamental spaces of a matrix. So there are four distinct important vector spaces associated with any matrix and its transpose. And these are called the fundamental spaces. Which are they? It's the row space of A, which is the space spanned by the row vectors of A, the column space of A, it's the space spanned by the column vectors of A, the null space of A, it's the space formed by the solution to the system A, x bar equals 0 bar, and then the null space of the A's transpose, which is the solution space to the system A transpose x bar equals 0 bar. Okay, right, so the next Theorem 5 tells us a little bit about the relationship between the rank of a matrix A and its transpose. So if A is any matrix, then its rank is always equal to the rank of its transpose. Okay, so look at the rank of A. The rank of A is the dimension of the row space of A. Likewise, the rank of A's transpose is the dimension of the row space of A's transpose. Right, now we know that the dimension of the row space of A's transpose is pretty much, you take A's transpose and you go and write down the reduced row echelon form of A's transpose, and you go and count the number of leading ones. And counting the number of leading ones is also going to give you the dimension of the column space of A's transpose, because the column space also corresponds, the dimension of the column space also corresponds with the number of leading ones. Now the column space of A's transpose, remember, it is the space spanned by the column vectors of A's transpose. And the dimension of that space it's the dimension of the column space of A's transpose. Now the columns of A's transpose happen to be the rows of the matrix A. So therefore, the dimension of the column space of A's transpose is the same as the dimension of the row space of A, because the columns of A's transpose, it's exactly the same space, or the columns of A's transpose, the space spanned by those columns, is exactly the same as the space spanned by the rows of A. And so the dimensions of those two things are the same. And we know what the dimension of the row space is. We said that that is the rank of A. Right, then another definition, if W is a subspace, if W is a subspace of Rn, then the set of all vectors in Rn that are orthogonal to every vector in W, that is called the orthogonal complement of W, and it's denoted by W with that little sign there. Okay, so basically what is it? That the orthogonal complement of W, it's the set of all vectors in Rn such that these vectors are orthogonal to all vectors in the set capital W. Right, when are two vectors orthogonal? They're orthogonal if and only if their dot product is 0. All right, that brings us to Theorem 6, which again says something about orthogonal complements. If W is a subspace of Rn, then the orthogonal complement of W is definitely going to be also a subspace of Rn. The only vector common to both W and the orthogonal complement of W is the 0 vector, And lastly, the orthogonal complement of the orthogonal complement of W is W. All right, now firstly, why is the orthogonal complement of a subspace W, why is it itself a subspace? Right, so let's quickly look at that. It's not difficult to see that. All right, so let's take two vectors in the orthogonal complement of W, and let's take any arbitrary vector in W. So we need to check that the orthogonal complement of W is closed under addition. So we take the two vectors, we sum it, we get a new vector, and let's see if this vector is still in the orthogonal complement of W. It's only the case if it is orthogonal to every vector in capital W. So let's take the dot product of that. So we know the dot product of that is, according to my rules, is that it's the distributive law. Okay, and we know that the vector, both these two vectors are in the orthogonal complement of W. So they both are orthogonal to every vector in capital W. So we have that X is orthogonal to W and Y is orthogonal to W. So therefore we get that is 0. So it is definitely true that the sum between these two vectors is going to be in the orthogonal complement of W. All right, so to check scalar closure under scalar multiplication, take a scalar multiple of the vector x bar, and we are going to check if it is still orthogonal to every arbitrary vector in capital W. So by the scalar multiple dot product equations, we get basically that then becomes the scalar multiple of the dot product between those two vectors there, and because x is orthogonal to W, we get that's alpha times 0. Therefore, we get 0. So therefore, the scalar multiple of any vector in the orthogonal complement of W is also going to be in the orthogonal complement. All right, so therefore, alpha x bar is definitely going to be in the orthogonal complement of W. So the orthogonal complement of W is a subspace. It's a subspace of Rn. Okay. Right, so let's look at the proof of the second property. The only vector common to W and its orthogonal complement is the 0 vector. Right, let's look quickly at the first case, where W is the subspace containing only the 0 vector. So let's see what happens there. If W is only the 0 vector, then we are done. Because the orthogonal complement of W also contains a 0 vector, and so the intersection between W and its orthogonal complement is only the 0 vector, so then we are done. So let's take the vector U that lies in the intersection between W and its orthogonal complement, and now our aim is to show that in fact this U vector is the 0 vector. Okay, so let us assume to the contrary that U is a non-zero vector, and it's in the intersection between W and its orthogonal complement. All right, so let's take a vector from W with the exception of the vector U bar. Now, because W is a subspace, it means basically that if you add the vector W to the vector U bar, remember U bar is also in W, it means the sum is also in W. Now let us consider the dot product between those two vectors there. Where is U? U is in both W and W's orthogonal complement. That means that U must be orthogonal to every vector in W, because U is also in the orthogonal complement of W. Right, now we said also that this vector is in W. So therefore U must be orthogonal, because U is orthogonal to every vector in W, U must be orthogonal to that vector there. So therefore, if you take the dot product between those two vectors, that's going to be 0. All right, so working out that dot product, we get this dot product here. Now, where was W from? This W, it's from that set there. And where's this vector from? It's from both W and the orthogonal complement of W. So therefore, U has to be orthogonal to W as well. Okay, so because that is orthogonal, those two vectors are orthogonal, the dot product is 0, and the dot product of the vector U with itself is the norm of U squared, and that's equal to 0. Righto, so therefore, what do we know? We know that the norm of the vector U is 0, and the only way that the norm of the vector can be 0 is if that vector itself is in fact the 0 vector. Right, before moving on, we want to look quickly at this problem, because this is actually, we need this. What this says is that if I go and look at the subspace W and I go and find a basis for the subspace W, we know the span of those basis vectors is the whole W. Then we say that a vector is in the orthogonal complement of W. The only way that can happen is if the vector V is orthogonal to every vector in the set of basis vectors. Okay, that's the only way that a vector can be in the orthogonal complement of W. It has to be orthogonal to every one of the basis vectors. Alright, so to prove from left to right, we take a vector to be in the orthogonal complement of W. And what does it mean for V to be in the orthogonal complement of W? It means V is orthogonal to every vector in W. Alright, so that means that V is the dot product of V with W bar is 0. And it is true for all W bar in capital W. Right, now this implies that V is orthogonal to every Wi. And why is this? Because remember that each Wi is in capital W. Each one of these vectors each one of those vectors is in capital W, right? Because Wi bar is part of the basis, and a basis is always part of the vector, the subspace that it spans. Okay, so we've proved that from left to right. Right, so we proved from right to left there. So what we're going to do is we're going to assume that V is orthogonal to every Wi. Then we're going to take a vector W bar in capital W. Thus, we can express W bar as a linear combination between these vectors here, because it's in the span of that basis vector set. Right, whence, so if we take V and we take the dot product of V with W bar, then we get Okay, so we get the distributive law of the dot product. So we're taking the dot product with that, the dot product with that, plus all of that, dot product with that. Okay, and we also know that V is orthogonal to every Wi. So that whole dot product is going to be 0, and what does that imply? It implies that this vector V is going to be orthogonal to every vector in capital W. So V is in the orthogonal complement of W. All right, so I just want to quickly, I'm not going to write down a formal proof, but I just want to quickly look at why is the orthogonal complement of the orthogonal complement of W. So in other words, why is it that if I take the orthogonal complement of W and I look at that orthogonal complement of and if I look at the orthogonal complement of this whole set here, why is it that it is in fact, why is it that it is W? If I take that orthogonal complement. Okay, so let's look at the property 3. The orthogonal complement of this set is W. Okay, now I'm not going to write out a formal proof of this. I'm just quickly going to go through why that is the case. So what we do is we choose a basis for the vector space for the subspace W, and there we've got the basis vectors W1 up until Wm. So these are all the basis vectors. Okay, so we want to determine the orthogonal complement of that set there. All right, so how do we do this? We want to find all the vectors that are orthogonal to every vector in that indicated set. Okay, and how we do that is, you pick a vector from that set there, and then we just want to go and find all the vectors that are orthogonal to V. So V is just an arbitrary vector from that set there. Right, so having picked the vector V from this set, okay, we also just define these vectors here as these vectors. All right, now when is a vector V in the orthogonal complement of W? It's on the orthogonal complement of W if it's orthogonal to every vector in W. And that we said only happens when this V is orthogonal to every vector in the basis of W. Alright, so basically the dot product of V and all of these vectors, or the dot product of V with every one of these vectors has to be 0. So what does that mean if we go and write all of this in matrix notation? Alright, so in terms of matrix notation, if you go and write that down, you get basically that this vector, which is my vector V, if I multiply that, if I take the dot product of that vector with any one of these row vectors, it always has to, the dot product must be 0 in each and every single case. So what are we actually saying? We're saying that this vector here must in actual fact be in the null space of this matrix. it must be in the null space of that matrix. So V is in the orthogonal complement of W only if it is in the null space of that matrix there. So that's basically the same as saying that, again, I want to reiterate it, that the orthogonal complement of W, if a vector can only be in there if it is in the null space of this matrix. So what is the dimension of that null space, or what is the dimension of the orthogonal complement of W? Now note that these rows are form basis vectors for the row space, and those are basis vectors for the subspace W. So if we're going to work out the reduced row echelon form of this whole matrix here, we are going to get, we can't get 0 rows, right? Because that's going to imply then that one of these row vectors is going to be a linear combination of all the other vectors. And we already said that these row vectors form a basis. It's the basis for the subspace W. So that implies that the rank of this matrix here is going to be it's going to contain m vectors, right? And the rank added to the nullity is always equal to the number of columns, and the number of columns in that case is n. So the dimension of the orthogonal complement of W is going to be n minus the rank of that matrix, which is n minus m. So the dimension of the orthogonal complement of W is fixed at n minus m. Right, so let's take a vector y to be in the orthogonal complement of that set. Now, because y is in the orthogonal complement of this set, it means that y must be orthogonal to every vector where that vector lies in the orthogonal complement of W. All right, now forming again the same matrix type equation there, if we form that, set up that matrix equation, then again every vector that's chosen from the orthogonal complement of W, if it has to be orthogonal to each one of these row vectors. So again, it has to be orthogonal to all these rows. Okay, which means that this vector here is in the null space of this whole matrix here. Now, to determine the null space of this matrix here, what we're going to do is we're going to reduce this matrix to its reduced row echelon form, and again these rows here, if we reduce all of them separately, we take that section of the matrix and we start reducing it. Again, we are going to get m leading ones there, and if this row doesn't reduce to a 0 row, that is going to mean that we have in the reduced row echelon form m plus 1 leading ones. Okay, so I will then get a general solution for this whole system here that is going to have because there are m plus 1 leading variables, it is going to give me it's going to give me a general solution with it's going to give me a general solution that is going to have n minus m plus 1 free variables. So in fact, there's going to be a general solution to that matrix system that is going to have n minus m minus 1. It's going to be a general solution that's going to have that many free variables. Now this general solution that I obtained with n minus m minus 1 free variables, if I take it and I plug it into this matrix system here, plug in those variables there, it's also going to satisfy this matrix system here. So for that matrix system, I've constructed a general solution that has got n minus m minus 1 free variables. But here I've said that the only general solution that I can get there is going to have n minus m free variables. So that's a contradiction, because I can only get n minus m free variable general solution there, but using this system, using this system here, I can construct a general solution that's got n minus m minus 1 free variables. So therefore, what does that mean? Okay, so basically, if I take the reduced row echelon form of that this matrix here, then basically this row has to reduce to a 0 row, which implies that that row is a linear combination, of all these rows. So what does that mean? It means that this vector here is in the span of those vectors, which we said was the set W. So we've proven that whenever a vector y is in the orthogonal complement of this whole set here, then it must in actual fact be in W. So the orthogonal complement of the orthogonal complement of W is